going to be talking about the difference between r, which we learned about before, and r squared. So first, I'm just going to introduce the concept of r squared and why we need to understand it. Why can't we just square r, right? And be like, haha, that's r squared. Well, we want to know what the meaning of r squared is, right? And so in order to get to the meaning of r squared, we have to understand that sum of squared differences is actually going to split apart into different ways. And so we're going to learn how to parse the different parts of the sum of squared differences. Then we're going to talk about what r squared means for a very strong correlation and what r squared might be for a very weak correlation. All right, so one of the reasons why practically you'll need to understand what r squared is that often when you do a regression on the computer, either in SPSS or Stata or any of those like statistics packages, they will often give you r squared as one of the outputs, right? And you might be looking at it and be like, why are they giving me r squared? And so we want to know, what is the meaning of it? Why is r squared? Why not just have r, right? Often if you just find the correlation, you'll just get r. But if you find the regression, you'll get r squared, right? So it's like, what's the deal, right? And r squared really is just r squared, right? But there's a meaning behind it. And I want to just stop for a moment and say, well, it's sort of like the difference between feet and feet squared. They mean different things. It's not just that you could square the number and be like, well, it's just the number squared, right? It's not just about the number, it's also about the actual unit. You have to understand what the unit is, because feet is a measurement that just examines length, right? But square feet now gives you area, right? And those are different things. They're obviously related to each other, but they're very different ideas. And so because of that, you need to also not only know like how to calculate r squared, but also know the meaning of r squared. Okay, so in order to understand the meaning of r squared, we're going to need to parse the sum of squares. Remember, the sum of squares that we've been talking about is something like x or y, and the difference between x and x bar, or the difference between y and y bar, right? And squaring all those and then adding them up. Sum of squares, right? And when we say sum of squares, you might hear the term that this is about variability. Sum of squares talks about variability. And it's because you're always getting that deviation between your data and the mean, right? And so sum of squares is often an idea that is highly associated with variability, right? So another way of thinking about parsing sum of squares is parsing variability, because variability comes from a variety of sources. And here we're going to talk about a couple of those sources and how to figure out, okay, this variability comes from that, but this variability comes from that. And then when you put it together, you have total variability. Now, total variability is going to be indicated by SST, sum of squares total, right? And this idea is all the variability in this system, so all of the variability. Now, we're going to take that and parse it, split it apart into two pieces. They're not equal pieces, but they're just two different places that variability comes from. One of the sources of variability is always from this relationship between x and y, and that can be explained by the regression line. So this is sum of squares from the regression, right? So that's going to be the idea of that sum of squares. This one is going to be the leftover sum of squares. So there's going to be some variability left over that's not explained by the regression line. And that's sum of squares error. Now, when we say error, we don't necessarily mean that we made a mistake, right? So it's not that we made a mistake. It might be that we made a mistake. But error often just means variability that's unexplained. We don't know where it came from. We don't know if it's because there was some measurement error. We don't know if there's just noise in the system. We don't know if there's another variable that's causing those that variation. So sum of squares error just means variability that we cannot explain, right? It doesn't necessarily mean that we made a mistake. Oftentimes, that's going to be how statistics uses that word error. It doesn't mean that we made mistakes. It might be. But it just means that it's variability that we don't know what to do with. We don't know where it came from. We have no explanation for it. So to break this down, you could see that this is sum of squares total, and that's usually what we get from looking at the difference between y and just like the mean, right? Because that's like the classic sum of squares, right? Because the mean should give us some information about where y is, right? But it's not every single point is going to be at the mean, right? So that's like error, but that's the total error. Some of that error, some of that variation away from the mean can be accounted for by regression. Like here, it's farther up from the mean. So so the numbers are all bigger than the mean, and down here the numbers are sort of smaller than the mean, right? But here, this is the residual error, and this we've already looked at before. So you could also think of it as residual error, where it's the rest of the variation that's not accounted for by that nice regression line that we found, right? So we could think of this as this is sort of the explained variability, right? So this is explained. And what explains this variability? The regression line, right? The regression line says, oh, it's going to vary systematically like this. The residual is what we call unexplained variability. We don't know where it comes from. We don't know if it's real error, just variability in the system. Maybe it's caused by another variable. We have no idea. And when you put the explained variability and unexplained variability all together, you get total variability. Okay. All right. Now let's break down specifically and mathematically what is sum of squares total, what is sum of squares residual, and what is sum of squares error. I want to give you a picture of what these things are, okay? So first, let's talk about sum of squares total. Well, one thing we'd probably want to do is get a rough idea of what the mean is. And so let's say the mean is something like this, right? And so I'm just going to call that y bar, because that's my mean of y, roughly. Sort of closer to these points, but these guys are sort of farther away, so they're pulling it down, right? So I'm going to call that y bar. And I want to know, what is the sum of squares total? What's the total variability that you see here? Now, because we're squaring all these differences, we're not just interested in sort of that residual idea. We're interested in, you could almost think of it like areas of little squares, right? So it's not only the distance down, but imagine that distance squared, right? And this area. So that is the variation of one, sum of squared variation of 1 point. Now imagine doing it with all of these. You create these squares, right? Some are big squares. Some are little squares, right? And you add up all those different areas. So here's a really little square, right? And you add up all of those different areas. That is sum of squares total. That's the total variation in our data away from the mean. Gosh, wouldn't it be nice if all our data like fell right at the mean? Because then we would be like, oh, I know how to predict this data. Just take the mean, right? But this has more variation than that. Okay. Now, I'm going to skip way over to sum of squared error, because that's one we actually already sort of know. In order to find sum of squared error, I need a regression line. So just going to draw a regression line like this. It may not be perfect, but something like that, right? And remember how we found residual? To find our residual, it's just the difference between my y, and not my y bar, but my predicted y hat, right? So these are all my y hats, and I want to know the difference between them. But we're squaring that difference, right? So instead of just drawing a line, we draw a whole square. And imagine getting that area, right? So that's the sum of squared residual or error for one point. But we got to do that with all of these points. Right? Find that area. Find that area. Find that area, right? And we add up all those areas. Then we get the sum of squared error, the variation away from the nice regression line, right? So here, this is our unexplained variation. This is our total variation. Now, what is this part? This is the variability that is already accounted for by the regression line. So this is the difference between the predicted y and y bar. Because here's the idea. If we just have y bar, we don't have a lot of predictive power, right? We're just saying, I don't know, y bar, it's just average, it's just the average. We only have one guess, right? The average, right? But if we have the regression line, we have a more nuanced guess. If I know what x is, I could tell you more closely what y might be. So I'm going to try to redraw my faux regression line. So pretend that's a nice regression line. So here's my y hat, but also here's my y bar. Right? And here, what I want to know is how much of the variability is simply accounted for by having this line. Having this line gives us more predictive power. How much of that predictive power is it? And so now we want to know, let's say for this point, right? This is now my difference. And then I'm just going to square that difference, right? And here's another point, right? But here, what's the difference? The difference is very, nothing, right? Here, what's the difference? So it's right here, this difference, right? And let me do another example, like right here, for this point, this would be the difference, right? So here, I'm looking at all of these. You could almost think of it as sort of the squared space in between my regression line and my mean line, right? So I'm looking at that. And that gives me how much of my variance in my data is accounted for by the regression line. All right, so that's roughly the idea. Now let's think about the actual formulas. And to help us out with that, I have a more nicely drawn version, not my crappy dots. But now you could see sort of, okay, so here's the differences, the squared differences between my actual data points and my mean, right? And so here are all my squared differences. Here's that same data. It's the same data from before, except now we're looking at differences from the regression line, not the mean line, right? Excuse me. And here, we're looking at differences between the mean line and the regression line, right? So now let's write these things down in formulas, in terms of formulas. So in order to find the sum of squares total, let's think about what this is as an idea. Okay, we want the sum of squares, so I know it's going to be something sum of squares, right? Like all of these guys are going to be like this, right? So I could already write that down. SSR will equal, the sum of something squared, right? And here this is going to be, SSE is going to be the sum, oops, I have like an extra squiggle, the sum of something squared. Okay, so we already know that's going to be the same for everybody. Here we have for every y, give me the difference between that y and the mean, and then square it, right? And get that area. Get all these areas, and then add them up. Right? So that's just y minus y bar, right? That's all. And so if we wanted to fill this out, we would know, this just means for every single point that we have, get y minus y bar, and then square it. Add them up, right? That's that idea. So that's sum of squares total. Sum of squares residual, actually let's go over to sum of squares error. I sometimes call it also sum of squares residual because this is the idea of the residual, right? Remember the residual was y minus y hat, right? And so we're squaring the difference between y and y hat. Right? So that's really easy. Y minus y hat. Ta-da! And then if you wanted to fill it out, you could obviously put in the i's as well, just so that you know you have to do that for every single point. And then for the sum of squares for the regression, I know, that's why they call it sum of squares E instead of sum of squares residual, because it's confusing with the R, right? So this one is sum of squares regression. I like to think of this guy as like sort of the good guy, right? So it's like you want to be able to predict X and Y, and this guy helps you because he sucks out some of the variance. This guy is the leftover that I don't know what to do anything about. So when we talk about the regression, we're talking about the difference between y hat and y bar, right? So that's y hat and y bar, right? And so, and you could obviously do that for each point. So there you have it, the formulas for these. But if you understand the ideas, you could always like just sort of think to yourself, okay, what is this a picture of? This is a picture of the difference between the data points and y bar. Here it's a picture of the difference between the data points and y hat. Sometimes it may be confusing though, because you might be like, wait, bar, hat, which one is it, right? All you should do is sort of go back to the picture and think to yourself, am I talking about total variance or variance after we have the regression line, right? Okay,